You have R, you have a leaving group, you have a nucleophile. It can be negative charge, it can be neutral, all of them on there, and you get substitution. Okay. You get your well, so far, every example we've seen, the leaving group has been a halogen. It's been, fluorine, chlorine, bromine. Nothing special needs to be done to these guys to get them to leave. They don't mind leaving with a negative charge. Okay? But if your leaving group is an alcohol, then you're going to beat on it some more. If it's a halogen, this happens easily because bromine doesn't mind having a negative charge. But if you have an alcohol, this is not going to happen. OH minus is not that stable. It's a strong base. Remember, strong bases aren't favored. They tend to form weak bases. So this is a no-no. So you got to add an extra step. Unlike a halogen, it just leaves. With the alcohol, you have to add an acid to make it a better leaving group. So we can still do substitution reactions, but you have to add, I don't know, let's say HCl. You have to add an acid, a pretty strong acid, okay? And then you're going to get substitution. Okay? But you can't just add Cl minus. Cl minus won't get this out. But what happens is proton transfer. Okay, and so after the proton transfer is taking place, you have this and this. Okay. Now this is a great leaving group. Okay, it's a neutral molecule of water. So this can leave and form a carbocation and water. And then the nucleophile can attack. And the last step we have being to find a problem. And again, we don't care about the inorganic product water. So this would be a three-step process. This is an SN1 type mechanism, right? Because you form a carbocation. But unlike the halogen, there's an extra step ahead of the leaving group leaving because OH minus is not going to leave. So if you add an acid, proton, then the OH minus doesn't have to leave. Then you can leave as a neutral water molecule. Okay. So do you see how it's a little bit different? Protonation first, loss of leaving group, and then nucleophilic attack. Okay. You don't have a proton transfer step in the end. Now this is three dance steps, right? Proton transfer from this guy to this guy, loss of leaving group, and then nucleophilic attack. Do you see how you can get 4 steps? You could get a carbocation rearrangement. So could you do this? If I gave you this complete reaction, and you notice the carbon skeleton is rearranged. The OH is here, okay? Actually, we're not going to rearrange it. Well, we're not going to rearrange the carbon skeleton. How about that? We won't do that. So these are together. And what we're going to get, though, carbon skeleton will be rearranged. But you expect the substitution to take place here, right? But the substitution will take place on this carbon, okay? In other words, you're going to have this cyanide here. And again, water. Okay. So can you come up with mechanisms, and all 4 of the steps will be involved,
If either the carbon skeleton rearranges, or if the carbon has a leaving group does not end up with the nucleophile, then you know some funny business is happening. The carbocation is rearranged. So this end carbon has the leaving group, but the middle carbon ends up with the nucleophile. So you know that some rearrangement took place. Not the carbon skeleton in this case, but a hydride shift took place. So 1,2 hydride shift. So I'll give you this. I'll say this is an SN1 type mechanism, and then I'll ask you for the steps. Okay. So with arrows, you could I'll try to remember what the wrong pairs. You do this. Okay, so this would be a proton transfer. This usually, proton transfers are usually pretty darn fast. They take place really, really quickly. Okay, now you have a great leaving group. So this bond can break. Okay. But minus H2O if you want to, doesn't matter. When that bond breaks, you get this carbocation. Remember, there's a hydrogen here. I haven't been drawing it in. Here's a hydrogen here. This is the first 3 carbocation. If you can rearrange, you will. So that was the next step. So this hydrogen with the pair of electrons migrates. That's a 1,2 hydride shift. And now we go from a first degree carbocation to a third degree carbocation. And then the final step is nucleophilic attack. Remember the first step? We formed a cyanide ion. Because this bond broke. So the last step is attacks, and you get your final product. So that's kind of messy. Just that OH won't leave by itself. It has to be a protein. So these reactions only take place if you have a fairly strong acid. And lots of times they'll use sulfuric acid, just to protonate. That's all it does. It won't do anything else. So you might see this reaction. And I'm not asking for the mechanism in this case, but you might just see H+. That means we dumped in some acid. It's usually H2SO4. And then you'll see like sodium cyanide. So basically, the sulfuric acid can protonate. It can't act as a nucleophile though. It's too weak. So it just protonates. So this would be used to protonate this. Okay. And again, I'm not going to ask you for this kind of mechanism. It's a bit messy. Then this could leave, form a carbocation. This could rearrange. And then this cyanide, you have sodium cyanide, then will attack carbon and give you the final product. So this would be more, not a mechanism question, but what is the product in this reaction? And so you tell me this is the product. Okay. So with these alcohols, lots of times they'll use sulfuric acid just to protonate the oxygen, just so water can leave, just so you can form a carbocation. Now, sometimes you'll have 2 mechanisms going on at the same time, so that's not that unusual. Okay, you learned that for SN1, these guys react the fastest. First degree, a little bit slower. Second degree, slower, and the slowest for the SN, oh, we got it back, SN2. Sorry, tonight I'm just not there. So, don't botch it up. Everything I talked about tonight, just reverse it, and it's probably correct. So methyls react as fast as the stirrup constraints. Leave fluid comes in from behind. First degree a little bit slower, slower, and slower. Okay. So basically, if you have methyl halide or first degree halide, it almost always goes by the SN2 mechanism, almost always. And then third degrees almost always don't go by this mechanism. Second degree, third degree. So let's just put SN2, it's going to be these guys here. These guys like to go by SN2. And the SN1 is the reverse, right? If it's SN1, then you copy this down again. It's this one. So try to keep that straight as best you can. Very important to keep it straight, don't let you confuse it. This is the reactivity for SN2, this is the fastest, third degree is the slowest. For SN1, this is the fastest, this is the slowest. If it's methyl halide or first degree halide, most of the time SN2. If it's a third degree alkyl halide, most of the time it's going to be SN1. What about second degree? Well, you get a mixture. Some of it will go by the SN1, some of it SN2. It's hard to say. You might get both mechanisms occurring simultaneously. And that's what I mean. You get a mess a lot of times in organic chemistry when you make something. It's not that hard to make something. It's just that when you make something, you make a bunch of other things with it. And so then you got to purify that mixture. Especially if it's a pharmaceutical drug, you can't be given side products along with the drug because some of these side products might be very toxic. So you got to purify these materials. So that's, that's what the game is play here. And as you'll see next chapter, besides substitution, you always have elimination reactions competing with substitution. So that makes it a bit more complicated. And that's the next chapter.
Why did you box those two together again?
Because they can go either by both the SN2 or the SN1. Sometimes you'll have half will go by one, half will go by the other. These pretty much go by the SN2, okay? Because the carbocations formed by this, carbocation formed here aren't stable, see? So these go by the SN2. This goes by the SN1 because third degree carbocations are formed and they're stable. They will not go by SN1 if you have these guys. You're not going to form a carbocation. These like to go by the SN2 because the SN2, you got stirred problems. The sucky. The nucleophile comes in from behind, you have 5 groups from the carbon, and there's some crowding. So this is not going to be crowded, this won't be crowded. But if you try to do the SN2 mechanism of this, you got a nucleophile coming in from behind, you got these groups here, they're in the way. It's not going to go. It's not going to go by the SN2 mechanism because of crowding effects. So pretty much crowding determines the rate of SN2 mechanisms. These are uncrowded. They favor the SN2. These tend to be more crowded in the transition state. They don't like to go by the SN2. They rather go by the SN1. So crowding effects determines this reactivity. This is the most reactive for SN2. This is the least reactive. Electronic effects, stability of carbocations determines the speed of the SN1. This guy reacts the fastest because this leaves you form a third degree carbocation. This reacts the slowest, actually not at all. Because this leaves you get a methyl carbocation which is extremely unstable. So these two will not go by the SN1. This guy will. These two go by the SN2. These guys kind of straddle things. So you can get a mixed bag. Okay. Comments, questions? You guys are survivors, I tell you. It's 3.5 hours. If the nucleophile is, well, let me backtrack. This mechanism I just showed you with alcohol was the SN1 type, but actually, you can go by two possible mechanisms, as you might guess, SN1 or SN2. It just depends on the structure of the R alcohol. So let me show you where it diverts. Here's where it does not divert. The first step, you get a protein. You're going to have an acid. You get a protein. That's a no-brainer. Okay. Now, what happens next depends on a bunch of different things. The size of the alcohol, the solvent polarity, the strength of the nucleophile. But let's take a powerful nucleophile. Let's say we have a powerful nucleophile. OCH3 minus. Again, this is going to be rude. It's not going to wait for this to leave. It's going to come in, kick this out, and you're going to get a substitution right here. So this is more like an SN2 type process. Protonation or proton transfer, if you want, followed by nucleophilic attack and loss of leaving group. Okay. So I guess you can do this. Okay, so proton transfer, somebody supplied an acid, some nameless compound, using sulfuric acid. So if you put sulfuric acid down, you're allowed to just write H+. Sulfuric acid spits out H+, and then the alcohol can attack it. So this is a proton transfer from H2SO4 to this. And then simultaneously, in a single step, this is a rapid equilibrium, you get this powerful nucleophile attack. Now suppose, instead of having this, instead of getting the SN2 type, suppose you have a weak nucleophile. So let's recopy this. Let's just recopy this guy. And we have a weak nucleophile. It's not going to be pushy. It's not going to be rude. It's going to be genteel, I guess you could say. This is neutral. It's not a powerful nucleophile. It's going to wait for this to leave in this slow step, form a carbocation, and then after that happens, then this comes in and attacks. Okay, and so you get this. What do you think the last step needs to be?
Proton transfer.
Yeah, proton transfer, just loss of ego. In other words, you can cheat, just do this. Flip that back in there. Outside, just put minus H+. Somebody pull off this hydrogen. You see, you get both the same products, whether you go by the top mechanism, SN2, or the bottom mechanism, SN1. And so which mechanism follows, it's hard to say. I'll even tell you, show me the products by SN1 mechanism or by the SN2 mechanism. Because again, it depends on a lot of factors. If this carbon was in here, this is the first degree carbon, let's take away this guy, it's probably going to go by the SN2 process. On the other hand, if this is a third degree carbon, it's going to probably wait for this to leave, form a carbocation, and then attack. Also, typically, if you have a neutral nucleophile that's leave, it waits for this leaving group to leave, then it comes in and attacks the positive center. If it's a powerful nucleophile using negative charge, it doesn't wait for this to leave. It just comes in right away and pushes this out. So the strength of the nucleophile makes a difference. And it's not all that clean cut. You're going to get mixtures. SN1 and SN2 mechanism. Okay, so with alcohol, just remember there's an initial step, a protonation step. Then it hits the road. Okay. Any questions or comments? There's one other trick that chemists have. They don't like carbocations. If they can avoid carbocations, they will do so. So that's one of the bad things about, say, this mechanism here. You're forming a carbocation. Okay? And can rearrange. And besides that, there's a bunch of side reactions that we haven't got into yet that carbocations can undergo. So you just end up with a horrendous mess. So there is a way sometimes to make this guy leave and not go through a carbocation intermediate. Okay? There's a special reagent called tosyl chloride. And tosyl chloride looks like this, if I can remember correctly. Okay. And the abbreviation is TSCL. Okay. This is an extra step, but if you can avoid carbocations, sometimes it's worth it. Okay. This, instead of adding an acid to an alcohol, using sulfuric acid, you protonate the alcohol. Then this bond can break, and you can get a carbocation. And then you can have that react in your products, but unfortunately, again, it does a bunch of other things. So there's another way to avoid this. Instead of adding an acid to an alcohol, they'll add tosyl chloride. Now, this mechanism is a bit messy, so just look at it. Don't worry about it. Remembering it, and I'm not very good kind tonight. Okay, I'm bunched up here. All right, so that's the tosyl chloride, okay? So what happens is, this is chloride is a good leaving group, so this will kick out the chloride. So Cl minus leaves, remember chlorine doesn't mind having that first. So you get tosyl chloride, when the smoke clears, you get this mess here. And Cl minus. I'm not going to ask you for this mechanism, so don't worry. Okay? This is a neutral molecule, this is a neutral molecule, this is a plus charge, this is minus charge, and we still have neutrality. And of course, then the next step is to pick out the hydrogen. Okay? Now, we're not forming any carbocation. This is and remove the hydrogen. This is a proton transfer. So you get HCl, and the compound of interest is this. You get this. And this is an excellent leading group. It doesn't need any help. Okay? Even a weak nucleophile will push this guy away. See? So the nucleophile will come in from behind, strong or weak, and just push this out. You don't have to wait for this to leave, form a plus charge. Even a weak nucleophile like water, for instance, we don't want water because it'll be the same starting direction. Let's take, I don't know,